Okay. Okay, so six already. Okay, so we have lectures this week, and then you have a break next week. So this week last week we finished off change of basis, similarity matrices, determinants. And this week we start an important part of the course, really the end of the linear algebra part, well, almost the end of the linear algebra part, which is about Jordan normal form, which will take a while, but there's things along the way that are useful in their own right, so that's good. And then basically the plan, so that's for this week and the first week after the break. We'll be talking about this kind of stuff. And then after that, there's a week on inner product spaces and permission and unitary matrices. And that leads us nicely into the group theory part, which is weeks 10, 11, 12, I think. That's the way it all out. I think that's right. Week 6. Okay. Maybe 9, 10, 11, 12. Something like that. Good. All okay? Any questions before we get started? That's all going. Right. And there's a quiz coming up, but it's not for a while, right? So I haven't written it yet. What do you mean? Quiz coming up? There's a in-person quiz. I think it's week 9. Is that right?
Is after break?
After the break.
If it's an after break, don't tell me about it.
After the break, so relax. Me too. It's not written. So. All right, great. So the plan for today is to talk about. This microphone seems really weird today. To talk about eigenvalues and eigenvectors, but from a slightly different point of view. And in fact, we'll see quite quickly that eigenvectors anyway is too restrictive for what we want to do, so we'll need to talk about what's called generalized eigenspaces, and then that'll move us into what's called the decomposition theorem, which is taking a linear operator and breaking it up into simple parts, and well, it's part 1 of the Jordan normal form stuff. Anyway, let me explain a bit more about that. So our goal, continuing in the same theme for a couple of weeks now, for a couple more weeks, is we're looking at endomorphisms. So we've focused attention from just arbitrary linear operators now to ones that go from vector space to the same vector space, right? Endomorphisms. And once we do that, we've explained a few times why we want to look at, when we look at the matrix of that endomorphism, we want to take the same basis in the domain and the codomain for various reasons, so we can take composition and all that kind of stuff. And our goal is to really try to understand what linear transformation, what endomorphisms look like. The same goal is expressed in terms of finding a basis B, which in a loose sense makes that matrix as nice as possible. I'll expand on that a little bit as we go. B is going to be finite dimensional throughout, so that we've got matrices. Indeed, if we formulate it purely in terms of matrices rather than bases, then it's saying that given a matrix, an n by n, not necessarily invertible or anything, just a matrix, n by n matrix in F, we're looking for a member of the similarity class, which was all the things P inverse APs with P invertible. We want one of those which is as simple as possible. And the connection between those is P, if you take P is an invertible matrix, so its columns form the basis. So the matrix of this linear operator with respect to that basis is going to be this P inverse AP business. Okay, so that's the connection between bases and similarity classes. It's exactly the same thing. Just different ways of looking at the same thing. Right, that's our goal. And to break that goal into two parts, the first is going to be, well, a very natural thing to do, in fact, and you do it over and over as you do higher maths things. The first part, you've got, so your linear operator has domain this space V, but it could well have, it could well preserve certain subspaces of V. So it could have, like it could map a, let's say a subspace called X or something. It might map X into itself. So that means that that linear operator could be looked at by looking at the restriction onto X. It becomes a linear operator from X to X. The subtle point there is, like you've got all the complementary possibilities of complementary subspaces, you want it also to be invariant on the complementary subspace, so that you can break it up into linear operator behaving on X and linear operator behaving on an appropriately chosen complementary subspace such that it's also invariant subspace. Anyway, that's what we're going to do. We turn just to jump to the, so it's already in our mind. These subspaces are going to be what are called the generalized eigenspaces, as we'll see. So it's a bit of work to do that. That's basically the goal for this week. Just to explain what that means, though. Well, I'll go through this a little bit more carefully in a second. But it means that now that with respect to that basis, so pick a sensible basis of V now where it has a basis of x1, basis of x2, basis of x3, and so on. And then with respect to, because it's invariant subspaces, the matrix of theta in that special choice of basis is going to be block matrices down the diagonal like that. So it reduces the situation to not understanding this big matrix, but understanding these little mi, m1 up to mk's. And then so that part of the goal is going to be fairly general. And then the next part of the goal, which gets a bit more specific then, and is a bit more subjective, I guess, as to what as simple as possible means. But anyway, within each of those blocks now, those invariant subspaces, we want to pick a basis of those invariant subspaces to make the matrix as nice as possible. And we'll say that later. You know, ideally you'd like to diagonalize everything, but that's just not reality. Right, I'm going to expand on all of those things now a little bit more. Okay, so these xi's, these invariant subspaces, now let's actually define that properly so that we're on the same page. Subspace X of V is called theta invariant. It's just clearly if theta of X is in X for all X in X. Okay, so what it means, here's V again. X was some subspace here. Some subspace over here as well in the domains and codomains, which are both V. Theta goes between the two. And what we're saying is theta maps X into X. I mean, it doesn't have to be injective or anything, but or surjective or anything like that. But it's mapping X back into X like that. So the point is, if X is theta invariant, then we can consider the restriction. That's in those tube questions where I was showing things restrict on the image and kernels and commuting operators and stuff like that. The thing you have to do was really prove. I actually have to take it. It's a a medical thing with my drink. Hello, James.
So Newton's always going to get like a string subspace.
I think all those things doesn't.
Well, like we're going to say that there's like a string subspace that is theta variable. You can always decompose.
You can always decompose theta to the sum, non-trivial sum of invariant subspaces.
As in more than just.
Sorry about that.
Yeah, mapping to a small. That's exactly what we're
As it, yeah, my
If you think about
always got a medical thing that's come up today, so I just
Yeah,
have
it
to
seems like.
keep an eye on the phone.
part of the cell.
Alright, so anyway, we can consider the restriction here, and for notation I'm just going to put a little X down the bottom to mean the restriction. Sometimes people put a bar and an X or something. All those kind of things mean the same thing. Anyway, the restriction.
Disjoint cycles
All good?
on the basis.
Alright, so I'm sorry always that I can't freeze stuff over here in this lecture room. But let's add a bit more to that. So if I can write, well, I can always find a complementary subspace Y, but the key trick is going to be trying to find a Y that's also theta invariant. So that's important. I just want to explain now that you get a block form for the matrix. So we'll take B1 to be our basis of X, B1, comma, up to B, let's say, K. And B2, our basis of Y, let's call that BK plus 1, so on. Then we can make a basis of V, of course. And the things to notice is because X is theta invariant, theta of VI is in the span of the B1 up to BKs, which is X, when I is between 1 and K. And on the other hand, theta of VI, if I is in the upper half, so to speak. So here I'm just using the theta invariance. So what that means is when I remember how we make matrix representations, we have to take theta, we have to apply theta to this basis, write it back in terms of the basis, and that gives the first column. So that's saying the first column, for example, is only going to have non-zero entries in the first K entries. I mean, some of them might have also been 0, but after the Kth entry, they're all definitely 0. And similarly, for all the entries in the first K columns, they're all just in that top K part of the matrix. And then for the lower guys, they're all in the lower right-hand corner of the matrix. So what that means is the matrix of theta. So I'm really just explaining this block form business I was talking about. It looks like this, with a K by K matrix with just some stuff in there. And then all zeros, and then down here, whatever it was, n minus K by n minus K matrix. Or n minus K plus 1, whatever it is. Used by that. And I'll just give a tiny bit more space to write that another way. another way of thinking of that is the matrix of theta restricted to x with respect to our first basis, the basis of x, and then the matrix of theta, with restricted to y with respect to this second basis. Okay, so the point is theta is completely understood by its two little bases there. So basically what we want to do is, as fine as possible, as refined as possible, decompose V down into invariant subspaces. But the trick is, you can, even if you find an invariant subspace, it doesn't mean that it's not immediately obvious how to find an invariant complementary subspace. That's the main trick. Okay, just some examples. 0 and V itself are always theta invariant because theta of 0 is 0, so that's fine. What about one-dimensional invariant subspaces? Well, let's work out what they are. So suppose we've got our one-dimensional generated by V, let's say, is one dim theta invariant subspace. Now, since theta of V is meant to be in X again, so we have something that's very, very familiar to you. Theta of V equals lambda of V. For some lambda in whatever the underlying field was. So the point is, one-dimensional theta invariant subspaces, exactly the same things as eigenspaces. That's why you look at eigenspaces indeed. So definition there, something familiar. We want non-zero for our eigenvectors. Otherwise, theta of V equals lambda V is true if you plug in V equals 0, no matter what the lambda is. Anyway, so eigenvalues and eigenvectors, you know what that means. I won't read through it. The lambda eigenspace is just the set of all lambda eigenvectors and 0 to make it an eigenspace, as a vector space, subspace. And importantly though, we're going to denote that by V with a little subscript. And later we'll put a little superscript for something called, so up the top, for something called the generalized eigenspace. So anyway, in the course that's going to be standard notation we'll use. Lambda eigenspace is that. Of course, it's the same thing as the kernel of theta minus lambda I. It's all the things such that theta minus lambda I applied to V equals 0. Well, it's a very familiar idea. Well, eigenvalues, eigenvectors, more familiar for matrices, but as we've already worked out, matrices and linear operators are basically the same thing once you choose a basis. All right. Any questions about that? All right. Let's remind ourselves how to find eigenvalues and eigenvectors. All right, so how does the process work? I mean, you already have in your head det theta minus lambda I and all that stuff. But let's go through that a bit more slowly. So theta of V equals lambda V, with V a non-zero vector. So that means lambda is an eigenvalue, V is a corresponding eigenvector. That's the same as saying that theta, red, theta minus lambda I, V 0 with V, so I'm just rewriting the same thing. And I here, by the way, just to emphasize, I is the identity. sometimes I might write that as ID for identity or something, but we'll just write it as I. It's also the notation for the identity matrix, but identity operator too, why not? That's the same as saying the kernel of theta minus lambda I is not equal to 0 because there is a non-zero vector in the kernel. That's what we're saying. And that's the same as saying theta minus lambda I is not injective. But that's the same as saying it's not bijective. Now there's a tiny subtle point there. Of course, saying it's not injective, that implies that it's not bijective, but I do want these to all be both ways, and so the both ways requires the rank nullity theorem. And that we're working in finite dimensions. So maybe I'll do it like this, going that way requires rank nullity. And just to say, when you've got just to pause on this part of the logic, if you have an operator in an infinite dimensional space, it is perfectly possible for it to be not bijective but still be injective. That's perfectly fine. You just have to not be surjective. In infinite dimensions, we don't have rank nullity, so you can't go back this way. So what that means is in infinite dimensions, when you start looking at, in later courses, when you do functional analysis, is where you'll see this. You can have things that are in what's called the spectrum of the operator, which are lambdas where this is not invertible. You can have things in the spectrum that are not eigenvalues, sorry. So you can have places where this is not invertible, yet there exists no eigenvector for that. I won't call it eigenvalue now, but for that spectral value lambda. But in finite dimensions, as soon as this guy's not invertible, it's not injective, and there is, so therefore, there is an eigenvector. Anyway, so it's just worth sometimes acknowledging where things would break in infinite dimensions. And anyway, that's the same as saying det theta minus lambda I equals 0, and that's what you have in your head, how to find eigenvalues. So the method for finding eigenvalues is, well, that's it. I don't want to write anything in the middle there. That's the technique. You first find all of the lambdas which satisfy that polynomial equation at the bottom. This is just a polynomial in lambda, once you expand it all out. For each of those eigenvalues, that's finding eigenvalues. And for each eigenvalue, just find the eigenvectors by solving the linear equations that you have to solve. All right, so you know all of that. I just squeeze this one in for here. I just want to say it before I forget. A useful proposition is that if you have eigenvectors that have different eigenvalues, so if all of those eigenvectors correspond to pairwise distinct, so lambda 1 is not lambda 2, is not lambda 3, and so on and so forth, pairwise distinct eigenvalues, then those eigenvectors are linearly independent. That's a good exercise, make sure you do it. You would have seen it last year. Anyway, so now let's give a quick, I won't go through the calculations, but let's just look at how you find eigenvalues, eigenvectors in some examples. As I say here, I'm not going to go through them because it's really, you do know all of this. In the first examples here, let's take it where the linear operator is already just given by a matrix, and then maybe at the last one we'll go through one where the vector spaces are more exotic and we have to make it into a matrix problem first. So anyway, here's ones where we just have matrices. Find all of the eigenvalues and eigenvectors. As I say, I'm just going to slide through this and just read what we do. So you first find the eigenvalues. Get theta minus lambda I. Boop, boop, boop. Calculate it nice and carefully. The hardest part of ever finding eigenvalues and eigenvectors is certainly finding the eigenvalues, because solving polynomials is incredibly hard, despite them, like with quadratics, you get confident that you can do it all. Cubics are sort of not too hard either, but once you get higher and higher, they get harder and harder, and to a certain extent, sort of impossible to solve with a formula.
Good thing we're in F1.
So in F5 is good, yeah, good. So because we're in F5, if someone just alerted us to that, if you had to try to solve this cubic, how could you do it in F5? Just try all the values. In finite fields, life is actually super easy in any given example. To find all of the roots of this, just start plugging in. Lambda equals 0, 1, 2, 3, 4. If none of them are 0, this guy has no roots, so there's no eigenvalues over this field.
Are we just plug in the values that are like factors of 3?
Yeah, so that's what we're saying. So in F5, indeed, you can plug in all the values and read it mod 5. Is that what you meant?
It's like, remember like, all the roots have to be like factors of the last term.
Oh, no, that's only when you're working over the integers. You don't know that the roots are divisors of 3 per se. And also, divisors of 3 over a field, everything divides 3. So that test that you have in your mind, that's just looking for nice rational roots of a polynomial whose coefficients are in the integers. If you want rational roots of a polynomial, then all of those, and let's look actually at integer roots. Integer roots of a polynomial, they have to divide the constant term. But that's not true otherwise. Well, I mean, it is sort of true, but when you're working over a field, everything divides everything. So you've got to check everything. Yeah. Okay, yeah, so be careful with that one. That's the integers over the integers. Very restricted, but useful. Now here we can just check everything. Oh, good, that's what I did. I just check all values. The finite fields in this context are easy. And we find that there's just one eigenvalue. Okay, good. That's fine, I guess. And it's 4, which is also minus 1. For some reason I want to say minus 1. And then for each of those eigenvalues, make your linear system. And we just solve away, and we find the eigenspace for this one eigenvalue is that one-dimensional thing, turned out. It could have been 1 dimension, 2 dimensions, or 3 dimensions in this case. We had a 3 by 3 thing. We only have this one eigenvalue, so there's some kind of deficiency here. We've only got this 3-dimensional thing, one eigenvalue, and only a 1-dimensional eigenspace. We'll come back to that later on. Here's another very similar example, this time working over F3. We just check this polynomial at the end of the day has no roots, so it has no eigenvalues. But then, of course, if you repeat that same question over different fields, like in F5, for example, this does have a root, because 2, for example, 2 squared plus 1 is 5, which is 0. So in F5, there is something like I mean, there is a I squared equals minus 1 thing. Over the reals, there'll be no roots. Over the rationals, no roots. Over the complex numbers, there'll be roots, so on and so forth. All right, so it really matters what field you're working over, of course. Yet another example. Go for complex numbers now. Well, the eigenvalues. This time, okay, yeah, so the complex numbers, life, or real numbers, or rationals, or whatever, life is harder, and you have to be able to magically see how to factorize your, in this case, cubic, and that's lucky, and, well, it's contrived rather than lucky. It's a question designed so that it does have nice roots. Normally, they'd just be a big fat mess, and then it's not that practical to do all of this stuff by hand. Yeah, good. Anyway, we ended up getting 2 eigenvalues. We computed a few eigenspaces. This time it turned out one of the eigenspaces was one-dimensional, and the other one, when we did the row reduction business, we got a 2-dimensional one. Okay. At the end of the day, well, we'll discuss it in a minute, actually. Yeah, any questions about it? So that's familiar, right? Just wanted to make sure we're all on the same page. Maybe I will do this one. Oh no, I've also got this auto-populated. Let's go through this one slightly more carefully. So all eigenvalues and eigenspaces for this endomorphism. So now it's written just, there's that slight extra twist in the question that we have to now first turn it into a matrix calculation and then do all the calculations. So we have to pick a basis. We'd be crazy, I think, to pick any basis other than, well, not crazy, but that looks like the obvious basis to pick, 1, x. And we just compute theta of 1 and theta of x, and there they are. And that tells us what our matrix representation is. There it is there. And now we're just back in familiar matrix world, and we just turn the handle, find the eigenvalues, solve some systems of linear equations, and we get a few eigenvectors. I guess just to emphasize, the calculations have been done in matrix world. 1, 3 is not really the eigenvector. The eigenvector is 1 plus 3x. The point is when you actually take 1 plus 3x and plug it into that formula up there, you will get, whatever it was, 1. You'll get 1 times that same thing back. And similarly, when you take minus 2 plus x, you'll get minus 4 times minus 2 plus x back. Alright, okay, good. I didn't think it so productive to go through those in real time, so there we are. But to continue on, so we want a name for this det A minus lambda I thing. So the characteristic polynomial of an endomorphism is, by definition, I'll use the notation p theta of, and I'm going to use x instead of lambda for the variable. That just avoids a bit of confusion later on. And that, by definition, is the determinant of, and you make a choice here whether you do xi minus theta or theta minus xi. But as I've said in this little comment underneath, it doesn't matter which one you do because you're always interested in when this thing is 0, so it doesn't matter if you've swapped it around. The reason I'm choosing xi minus theta is because then the coefficient of, the leading coefficient of x to the power of n, is a 1 rather than minus 1 to the n. It's just a bit nicer for the general things. But you can use whatever you like. Maybe just to emphasize that, if you wanted to take the determinant of this guy, well, that's minus 1 to the n times the determinant of that guy, because that minus 1 is actually in every single row, and you have to take it out by row linearity n times, and that's why you get the minus 1 to the n. All right, that's a characteristic polynomial. Good. And the point of the characteristic polynomial is if theta an endomorphism has an eigenvalue lambda in the field if and only if our characteristic polynomial, which is a polynomial with coefficients in the field, of course, so it's that lives in that thing, has root lambda in the field, i.e. p theta of lambda equals 0. Okay, so nothing big now. There's a bit of a discussion to make though. So we're going to certainly use eigenvalues to decompose our domain into these invariant subspaces. And if we don't have any eigenvalues, we're just kind of stuffed. I mean, and it's not just our technique stuffed, you're kind of just stuffed in general. And so to do that, like you either do one of two things. Like every field, like the real numbers, there is an algebraically closed field, so where every polynomial has roots in that bigger field, and that would be the complex numbers on top of it. But even for a finite field with 5 elements, there is an algebraically closed field for which every polynomial with coefficients in F5 will have a root in this bigger field. That bigger field has to be really big. It's not going to be a finite field anymore. Just like the complex numbers, it's going to be an uncountable field. Anyway, so that's sort of one solution, is just to insist that we work over algebraically closed fields so that the characteristic polynomial certainly has roots. Or you just say we're working case by case, where we're going to assume that our linear transformation theta is such that its characteristic polynomial not just has a root, but factorizes completely down into linear factors. So if we were working over an algebraically closed field, that would be the case. It would decompose all the way down into linear factors, x minus lambda 1, x minus lambda 2, etc., etc. But we don't really need to assume algebraically closed for that. We could be working over a different field, and just our endomorphism is chosen so that it factorizes properly. Okay. But just to sort of say, even if you were working over the reals and you wanted to study an endomorphism, it's no real loss to sort of enlarge your universe to work in the complex numbers, make calculations there, do what you have to do, and then make your deductions back for the real numbers later on as required. So often going to the algebraic closure is just a completely standard thing to do. That's what I'm saying here. So field's called algebraically closed if every polynomial of degree at least 1 has a root in the field. So of course the complex numbers is algebraically closed. That's the fundamental theorem of algebra. The real numbers are not algebraically closed, of course, because x squared plus 1 has no root. No finite field is algebraically closed. That's actually got a very easy proof. I don't know if anyone's seen it before, but it's really analogous to just to see how proofs get recycled. That proof that there's infinitely many primes goes as follows. You assume there's finitely many, you multiply them all together, you add 1, and that number's not divisible by any of your previous primes. So it's either prime itself or divisible by some prime not in the list. So it's that like super famous 3,000-year-old proof or whatever that there's infinitely many primes. And the proof that no finite field is algebraically closed is the same thing. Take the polynomial x minus the first element of the field, x minus the second element of the field, x minus the third, and product them all together. It's only finitely many. And now just add 1. That polynomial is in your field, but it doesn't have a root in your field because, you know, the first term vanishes, but you've still got the plus 1. So you're not algebraically closed. So the polynomial p of x or something equals this product over all elements of your field x minus that field element. So that's only a finite product. That's okay. Plus 1 has no root in finite field f. kind of nice seeing these same proofs getting recycled. And there is a theorem which, as I've said down the bottom, it's not hard, it's not difficult to prove, it just requires a bit of different language. You prove it more in ring theory, that every commutative ring has a maximal ideal, and then that shows that it's not like just general nonsense, but you need Zorn's lemma for it. So every field, there exists an algebraically closed field for which your given field is a subfield of E. Right? So it lives in, like the situation with the reals and then the complex numbers, that always exists. That behavior always occurs. And in fact, there's even a smallest such E, which means something about, roughly speaking, about containment, you know, the smallest up to containment. And that guy is called the algebraic closure. So given any field, you can make the algebraic closure, which is something unique up to isomorphism of fields. And for the real numbers, that would be the complex numbers. The actual details really don't matter, except just to know that there is that machine lurking in the background. Just to say, the complex numbers can be made even bigger. So you can, an algebraic closure for the real numbers, there's infinitely many of them, all these bigger versions of the complex numbers. But anyway. Alright, so that's more just the general knowledge, in a way. Well, we'll sort of need it in the background a little bit. But as I say, there's really two ways we could have proceeded. We could have either insisted henceforth that we work over an algebraically closed field, but that's got a deficiency because sometimes we want to work over a finite field and our linear transform, our endomorphism is just such that everything will work perfectly fine. It won't work, the machine won't work fine for every endomorphism where you're working over that finite field, but for some of the ones, it works perfectly fine. So instead, we're going to assume this property. So when I say that the characteristic polynomial splits completely, this is what I mean. So that and I'll always write it with these letters pretty much. So x minus, the lambdas are the distinct roots of the characteristic polynomial, and the d's are the multiplicities. All right. Okay. And as I say in brackets there, if we were working over an algebraically closed field, we're guaranteed that this indeed happens. Any questions about that? Yeah, so that's a subtle, that's where we're really needing a bit more to assume some stuff. Maybe that's a good point to take a little break anyway, and we'll continue on in 10 minutes. Any questions? Let's take a break.
Because they're not written.
They're drawing like curves, isn't it?
Yeah, because he's not written. He just draws a picture.
Well, yeah, but I do. I mean, it's not how I think. It doesn't. We do have analysis next time. I'm really just like, I don't need all this.
Analysis is better, but
Even eigenvalue. Yeah. What is the number of? I guess it's a matrix. That's not going back.
Because I put my hand up for a round blue on a whim.
Well, I was going to charge my phone. Yeah. This one, algebraic closure is pretty cool.
I'm not looking at
Yeah. I'll just leave it there for a second.
I've made a discovery there. Yeah, I'll do it later. I'm a bit concerned about the I need to go although I don't have time for that. It's not it's really not. Okay, this is fun. I'll do it later. Actually wake up. How long have you been sleeping? Because it needs all of one. Oh, come on!
We have test cases. We have test cases manually, and we have to write our own test cases, and some of the test cases are here. I'm like, fully, so you want Wait, that's like I think he will find it. Wait, is it? Is it?
Well, I left this last week and then I gave up on it because it was like, I don't know. I guess I left it here. Was this you?
No, some of them are about.
That was very kind. I'm very happy about it.
My friend, he has Simon question to you.
Okay, so observation. Oh, yeah, since the time comes, let's get started again. So, yeah, the characteristic polynomial splits completely. Which is going to be our running assumption. And by high school things, in fact. You know that you can write, well, from high school, or they're called Newton relations or something like that. You know, when you have a polynomial that factorizes, of course, by expanding out the factorization, you can write all of the coefficients in terms of the roots, right? Just by expanding out the factorization again and collecting equating coefficients. So since our polynomial was designed to have x to the n as leading power with coefficient 1, that's what it looks like. And the next thing you get the sum of the roots plus, and then you get all this junk, and minus 1 to the n times the product of all the roots. With everything with multiplicity. Okay, just from expanding the thing out. So now we can certainly work out that constant term. That's easy. P theta of 0 is, well, on the one hand it's minus 1 to the n times the product of the roots, but on the other hand it's det 0I minus theta, which is minus 1 to the n det theta. And so the first observation is the determinant of theta is the product of the eigenvalues with multiplicity. So we have to put the D1s up there. Of course, if the thing doesn't have eigenvalues, then you can't do this kind of thing. But you could always just go to a larger field, to the algebraic closure, make the eigenvalues there, and then, well, I mean, this formula shows that even though those eigenvalues might live in a bigger universe, like in a bigger field, like if we're originally in the reals, they're in the complex numbers, but when you form this product, you do get something which is just a determinant, which is something back in your base field. So magically, it would still have to, all the complex parts would have to cancel out somehow. Anyway, but that's good. That's the reason why that's true. And, then you've also got the sum of the roots with multiplicity, and that's the trace. But that one you have to think a little bit more about. I'll leave that as an exercise. Explain why the trace of theta is the sum of the roots with multiplicities, which is d1 lambda 1 plus ... plus dk lambda k. In other words, you add lambda 1 gets added on d1 times, lambda 2 d2 times, and so on and so forth. Multiplicity. Okay, so that one is in the tutorial if you have trouble working it out. Good. Anyways, that's just an observation. Useful to know. For example, if our endomorphism, if we were just told that our endomorphism had this characteristic polynomial, then we can read off its determinant and its trace. Its determinant would be minus 1 times minus 3. So that's minus 1 to the 3. Oh, sorry, determinant, no, I got my minus, I don't need my minuses. Oh, yes, I do, sorry. Because it's, no, sorry, I'm getting confused, doing two things in my head. So just look at the eigenvalues and take their product with multiplicity. So it's 3 squared times minus 5. Whatever that is in the, I don't know what field we're working over, but that's what it is. And the trace would be the sum of that would be 3 plus 3 plus minus 5. Okay, so you can read off traces and determinants from the characteristic polynomial. And indeed, if you're in a 2x2 situation, two-dimensional situation, then you completely, the trace and the determinant completely tell you what the characteristic polynomial is, because you've only got those two coefficients, because the first coefficient is a 1, the x squared. But in 3x3 and bigger, trace and the determinant and the trace alone don't determine the characteristic polynomial. Okay, good. Now let's talk about, so our theme is to try to make our matrices ultimately, or our endomorphisms as nice as possible. And indeed, the nicest possible would be diagonalization. If you can diagonalize something, for example, you can then find powers really easy. I mean, every calculation is trivial then. So let's quickly get that out of the way. So an endomorphism is called diagonalizable if there's a basis which makes it diagonal in that basis. And so it's the same thing as saying a matrix. So to say a matrix is diagonalizable then is the same as saying there's an invertible matrix P such that, I'll get my things around the right way, such that P inverse AP is diagonal. Okay. And the theorem that tells you exactly when something is diagonalizable, it turns out to be really easy, luckily. So theta is diagonalizable precisely when there's a basis of eigenvectors. So when there's sufficiently many eigenvectors, putting it a bit more intuitively. So the proof of that is as follows. So if theta is diagonalizable, then by definition there is a basis B everything is finite dimension, just to emphasize again. We're really restricting to finite dimensions now. Call them lambdas. We'll see in a few seconds that they are indeed eigenvalues. That is what that means. What it means to be a matrix representation, that exactly means that theta of bi is lambda I of bi. Precisely what it means for theta to have that matrix. So B is indeed a basis of eigenvectors. And at the same time we see that these guys are eigenvalues. And the converse is, well, same logic really. So take your basis of eigenvectors and then theta in that basis is diagonal. I mean, maybe we should just write it out. Okay. So diagonal is exactly the same as saying that there's a basis of eigenvectors. We'll make another statement about that soon. But before leaving that topic, I mean, of course, if everything was diagonalizable, then we'd be happy, but even over, there's nothing about algebraic closed or anything, just things aren't diagonalizable. So certainly there's not always a basis of eigenvectors, and here's the smallest example. Let theta be from, let's work over C, so there's no issue of algebraic closure worrying us. So C2 to C2 with theta of V equals 1, 1, 0, 1. Well, let's just work through this example quickly. Then det x minus xi minus theta is, so x minus 1, x minus 1, as well, so it's just x minus 1 squared. Pen's dying a bit. So there's only one eigenvalue, which is fine. Then quickly computing the eigenspace. eigenspace for lambda equals 1. Oh yeah, for notation I can write, instead of just writing v subscript 1, sometimes that looks a bit confusing to me, so sometimes I write v lambda equals 1 for the one eigenspace. You can just write v subscript 1 if you like. But anyway, this is, so we have to have y has to be 0 and then x is anything you like. So this is the span of E1. So certainly we're not diagonalizing it. And in fact, so here we're in the situation where, getting back to our earlier discussion of trying to break things up into invariant subspaces, we do have an invariant subspace. This is a one-dimensional invariant subspace. But no matter how hard you try, you can't find a complementary subspace which is also theta invariant. It's clear that you can't do that because if you could, it's one-dimensional, so it has to be an eigenvector, eigenvalue thing, and we just found there's no more eigenvalues or eigenvectors. So that's important to know. So in this example, while v lambda equals 1 is certainly theta invariant, there is no complementary subspace y, i.e. C2 equals v lambda equals 1 plus y, that is also theta invariant. And the proof would be, if so, then y is one-dimensional. Then theta of y equals lambda of y. Well, I'll just say then y has to be an eigenvector. From earlier when we just showed that all one-dimensional invariant subspaces were just eigenspaces. And that's a contradiction because there's only this one-dimensional eigenspace, so we can't find another one. Good. Okay, so what that means is for this particular tiny little matrix here, up the top there, that's the end of the story for that little guy there. That you're not going to, well, it's not clear what simplest possible means, but you certainly can't diagonalize this, and essentially, I mean, it's plausible enough in a way. There's no simpler way, there's nothing else in its similarity class which is nicer than that, basically. So that's actually going to form in the Jordan decomposition language, something like that is going to be one of the atomic building blocks, one of the sort of canonical forms that you can't improve on. Okay, great. I've just said another way of looking at our previous example is we can't just look at eigenspaces for our generalized eigenspaces. We have to look at something more. So our invariant subspace that we had for that previous example should have just been all of C2. Okay, so we couldn't have just taken that one guy because we can't find the complementary. So the smallest invariant subspace is all of C2 for that example. If you want to also have complementary invariant subspace. So it leads us into the idea of generalized eigenspaces. And so that, I guess, is new to us. So let's go through that. So we've got our endomorphism, just for notation, by the way. nth power means, well, if it was a matrix, it's just nth power of the matrix. But now, if we're in endomorphism, it means composition, which, as we discussed, is the same as raising a matrix to a power once you've got the same basis in. But anyway, so the definition for the generalized eigenspace is as follows. So, well, I'll write this first and then change it. That would be the eigenspace, but the generalized eigenspace has a k up here, and it's for some k greater than or equal to 1. So, so generalized eigenspace, it's not just killed by, it's not in the kernel of lambda I minus theta, it's in the kernel of some power of lambda I minus theta. It's a bit, we'll sort of start seeing why we're looking at that in a few minutes. Non-zero vectors in just some terminology. So non-zero vectors in the generalized eigenspace. Notice the lambda's up the top now in the notation. And there's also the idea of something called the rank of a generalized eigenvector, and that's the smallest k. So if you've got something where this is eventually killed for a high enough power of k, the k just before it's killed, that's called the rank. Or maybe the k where it is killed. Sorry, the first k where it's killed is called the rank of that eigenvector, generalized eigenvector. So if lambda I minus theta to the k, v is 0, but not the previous one. Then v is called generalized. I guess I'd say up here as well, lambda eigenvectors, but you don't care about the lambda, you just drop the lambda. Rank k.
K feels element.
No, k is just an integer here. For some k bigger than or equal to 1. So k is 1, 2, 3, 4. Natural numbers bigger than or equal to 1. So it's composition. We're taking this linear transformation here and composing it with itself k times, or if you like, just applying it to theta to v, sorry. K times, applying this guy to v, k times. Maybe just to do a quick example, instead of going straight into more theory. So for example, with k, with theta as above, the C2 to C2 example, let's make a really general calculation here. Let's start with we've got our only one eigenvalue lambda, so we'll look at I minus theta. And let's look at what that does to a general vector xy. That's, well, this was 0, minus 1, 0, 0. So that's whatever it is. By that, minus y, 0. And if we do it twice now, then again, same matrix again, times now what we had earlier. So I'm just squaring that matrix, so I've already done one calculation. And now we get 0, 0. So in fact that says every single vector in C2, for this little guy here, little example, every vector is a generalized one eigenvector. Okay, which is sort of what we want in a way, knowing that this matrix you can't decompose it further into invariant subspaces that are both, invariant, all invariant subspaces, so we get everything here. That's kind of reassuring. Okay, but let's quick proposition. Some things that are, more or less obvious, I guess. First of all, this is a subspace. We should quickly check that. Okay, we're calling it generalized lambda eigenspace. It had better be an actual subspace. The lambda eigenspace is a subspace of the generalized eigenspace. That's good. That's also clear. Like these are the things that get killed by k equals 1. So certainly that's a subspace. And if the generalized lambda eigenspace is non-zero, non-trivial, then lambda is necessarily an eigenvalue. So there is an eigenvector for that. But as we've already said, this could get bigger than the eigenspace as in that previous example. Eigenspace was one-dimensional. This guy became two-dimensional. It certainly contains the eigenspace. That. And finally, it was clear with generalized eigenspaces that they were theta invariant. This guy's also theta invariant. All of this is pretty easy to prove, luckily. So first of all, we have to say that we make 1 and 2 are exercises. It's about run out of time. No, let's make it again. So for 1, if x and y are in V lambda and lambda and mu are in the field, then, well, the fact that we're in the generalized eigenspace means that there exists a k1 and a k2 such that this guy is 0 and this guy is 0. Maybe I'll write it as cat for... I'll write it like this. Oops, that's a y. And that's for k bigger than or equal to k2. And so theta minus lambda I to the k of lambda x plus mu y equals, well, the first thing we're doing, even though we've got this high power, which makes things look like it's not linear, but of course it is linear. Composition of linear things is linear, so this is this, even with this K, which looks a bit more frightening, this is still a linear map. And then, of course, to make that 0, we'll just make sure our K is bigger than or equal to K1 and K2. The maximum, or bigger than the maximum of the two, or however you want to express that. Okay. Alright, so it's a subspace. I guess I should have said it has 0 in there first, so it's not empty, and then it's closed under the linear combinations. Maybe let's leave 2 as an exercise. 2 is the one saying that the eigenspace lives inside there. Oh, well, 2 is obvious. Maybe let me write it like that. Three, here's the one where saying that if our eigenspace is non-zero, then lambda is an eigenvector. So here, let's, so if V is non-zero with lambda I minus theta to the K equals 0, so that we're in the eigenspace, choose the smallest K so that lambda I minus theta to the K V equals 0, i.e. that's the definition of K being the rank. That then means so I'm trying to show that a lambda is an eigenvalue, sorry. So I have to find an eigenvector. So let W be this non-zero previous guy. And then, of course, lambda I minus theta applied to W is now lambda I minus theta to the K applied to V, which is by assumption 0. So W is a lambda eigenvector. So lambda is an eigenvalue.
If K is 1, do we take the
Yeah,
thing to be the identity?
Exactly. If K was 1, any endomorphism to the power of 0 is the identity endomorphism. Yeah. Like a matrix to the power of 0, by definition, that's the identity matrix. Good. So the point is, if K was already 1, then the V itself is already an eigenvalue. And finally, for the theta invariance, oh, there we go. Move that up. So if maybe get rid of this. I mean, the easiest way to see this is then since lambda I minus theta to the K theta equals theta lambda I minus theta to the K. So what I'm saying there is these are polynomials in theta, and polynomials commute. You know, one polynomial times another polynomial is the same as the other way around. We have. Because I'm trying to show theta invariance, so what I have to do is show that theta of our vector V, this guy is meant to still be in the generalized eigenspace. That's what I have to do. But to show he's in the generalized eigenspace, I have to look at this raised to some power, but I'm just going to take the kth power. this equals by what I just said. Just to be really clear, I mean, I'm just writing them next to each other, but there's a composition sign, I guess, there. As you like. This is theta lambda I minus theta to the k of v. So that's theta of 0, which is 0. So indeed, put a bracket around there like that. So indeed, theta of v is in the generalized lambda eigenspace. All right. Okay. Okay, so these things are definitely theta invariant. They're looking good for us. Now, yeah, look, there's a little bit more technical stuff for today. Just a few more minutes, really. The idea of what we're going to do next, well, we're going to need a few technical elements later on as well, but a little bit the moral of why we're doing them is that, first of all, when you're trying to compute the generalized eigenspace, so computing eigenspaces is really easy, but computing generalized eigenspaces, okay, it's also easy once you know what to do, but in principle, it's not that, on first glance at it, it doesn't look that easy because you don't know how high you have to take the k to do this. So, for example, for some generalized eigenvectors v, well, that generalized eigenvector might actually just be an eigenvector. So then k equals 1 works for that guy. But you take some other generalized eigenvector, like we did in our C2 to C2 example, and you need 2 up there. So the eigenvector 1, 0 in that C2, C2, that only needs k equals 1, but the one 0, 1, which is not an eigenvector, but it is a generalized eigenvector, needed k equals 1, k equals 2, sorry here. But in principle, on face value, when you look at it, for each different vector in your vector space, you might need a different power of k. It turns out you don't. There's a global bound on how big k can be, but that's the first goal, to understand that. Okay. Yeah.
So when you don't have when you have an algebraically closed field for all of this, you don't have an algebraically closed field, we can't necessarily say that eigenvalues exist.
Yeah, exactly. So the way we're going to get around that is to insist on our so instead of insisting a condition on our field, we're going to insist on a condition on our linear operator to assume its characteristic polynomial factorizes completely. This assumption is, so to emphasize again, there were 2 choices of how we
Again, I'm just like, how would we construct such a thing? Because we want to be able to do this for arbitrary linear operators.
Oh yeah, so you can't. For an arbitrary linear operator, there's no way of, you have to just assume it's an algebraically closed field. But it's more general to just say, let's assume our linear operator, its characteristic polynomial factorizes, because then we'll actually be able to work over, well, something more general is the wrong word, but we'll be able to work over non-algebraically closed fields when the linear operator allows it.
Could we work in the fact that even if we get non-fully factorizing characteristic polynomial and we look at the matrix polynomial, right? Could we look at an equivalent of generalized eigenspaces for that? We still get our invariant subspace difference in terms of you have some irreducible polynomial factor instance of theta, right?
Yep.
To the k, right? Would you still? So do you understand what I'm talking about?
Yeah. So if the characteristic polynomial factorizes into 2 parts,
yeah.
in over the non-algebraically closed field, but not linear, then you'll get an invariant subspace of the size of that polynomial and 1.
So you still get an invariant subspace decomposition, you just want the eigenvalues.
Yeah, that's right. All right, good. So anyway, for now, our first task is to get a slightly more user-friendly version for the generalized eigenspace. And in fact, this little lemma that we stake here is going to be used all the time. And here it is. So it's about images and kernels. Okay, it's a nice little thing. So we've got our endomorphism. First of all, if you're killed by something, if you're killed by theta, you're certainly killed by theta squared and theta cubed as well. Okay, so certainly these first two things should be basically obvious, but we'll write them down. The things we're going to be mostly interested in are when these chains. So let's just look at the first chain. So this first chain should be clear that it's true. But these can't all be strict containments because we're working in a finite dimensional space. So at a certain point, we're going to get that they start, two of these guys, consecutive guys, are the same. And then we're just going to need to check that they stay the same forevermore, and similarly with the images here as well. The images also can't be strictly decreasing because we've got finite dimensions here going down to 0 dimensions at the smallest it can get. So eventually there'll be a matching up, and then it's we'll just check that it stays stabilized forevermore. Anyway, all right, let's prove that. So for 1, let me just write down some statements for 1, even though I said 1 was pretty clear. So 1, if V is in the kernel of theta to the power of k, well then, let's just write that out. So certainly theta k plus 1, V equals 0, 2. So that shows all of those containments. The ones for the image are similar. And now let's do the third one, and then the fourth one is again similar. Okay, so of course it's enough to just prove what I'm saying there. Well, let's assume not. Since we know that from part 1, there's going to be something in the bigger one that's not in the smaller one. Okay, so since they're contained, to say they're not equal means what I just wrote then. So thus, theta k plus 2 of V is 0, but theta of k plus 1 of V is not 0, but that says with W being defined as theta of V, theta of k plus 1 of W is 0, but lots of buts, but theta of k of W is not 0. So, but that's exactly telling us that the kernel, this guy's not this guy. Contradiction. Okay, and 4 is similar. Well, maybe similar is not the right word, arguing with images instead of kernels. Anyway. Okay, so for any endomorphism, we always have this increasing chain for the kernels, decreasing chain for the images. Once the chain stabilizes, it stays stable forevermore. I think we we have time to do the next bit, which is basically once one of them stabilised, the other one has as well. So there's a bit of a compatibility with how it works. Okay, you can sort of start, maybe we can start seeing roughly, or just why are we going to possibly do things like this? These thetas are going to be replaced by theta minus lambda I. So we're going to look at each eigenvalue, and instead of the endomorphism theta, we look at theta minus lambda I. So then this is something about generalised eigenspaces, roughly put, like looking at higher and higher powers of this thing. Once we've got, and then we're going to use a rank nullity thing to put something as a direct sum of kernels and images. And images we're going to see become stabilised as well under theta minus lambda I. So we're going to get invariant subspaces where you've got a kernel and an image down the bottom. But not just the kernel and the image, some sufficiently high power of the kernel, well, kernel of a sufficiently high power is theta minus lambda I, and then the image of that sufficiently high power of theta minus lambda I. And they'll both be theta invariant by, once we unpack everything properly, and then we can do that for each eigenvalue. Okay, so that's like the sketch of what we're doing. But first, let's just tighten it up a tiny bit because we need it a bit tighter. All right, so let's say we've got our finite dimensional vector space, and we've got our M such that, well, then there is an M such that this happens. I already said that because it can't just keep going forever if it's finite dimensional. And moreover, well, this one, we already showed that this stabilises forevermore, but the key point is this one also is stabilised for that same M, and the next one is what I was just saying as well, that we get an internal direct sum now, not an external direct sum, so it's better than rank nullity, internal direct sum. And then basically they're going to be two invariant subspaces once we replace theta by theta minus lambda I. All right, let's do that. And then I think we can stop soon after that probably. Okay, so since we have our ever increasing chain, it has to stabilise at some point. Just to emphasise that, I mean that's because everything is subspaces. If it was just subsets, of course you could keep doing this inside a finite dimensional space, but they're subspaces, so each one, for strict containment, its dimension goes up by 1 each time, at least 1 each time. Okay, and so the M in the theorem exists. With the property that the kernel of this guy equals the kernel of this guy. Okay, so then kernel of theta to the k equals the kernel of theta to the m for all k bigger than or equal to m by the lemma. And moreover, now we've got to say something about the images, but we can relate images using rank nullity. The dimension of V is, this is the dimension of the kernel of theta to the m plus dimension the image. So that's applying rank nullity to, let's say, Tor or something, being theta to the m. So I'm applying the rank nullity theorem to that linear operator, theta to the m. But I'll apply it to some other ones as well. It also equals dim cur theta to the k plus, so that's for all k, that's applying it to this linear operator, but then the point is we know something about the kernels, so we also know something about the images. We knew that the kernels had stabilized, and so that's how we get our information about kernels, about images, sorry. So those two things, oh sorry, that wasn't dim in, that was dim cur. And those two, of course, tell us that these two guys have to be equal. This was for k bigger than or equal to m, of course. So the dimension of the image of theta to the k equals dimension of the image of theta to the m. Hence, since there's a containment thing, since one is contained in the other, and that one's that the image of theta to the k is contained in image of theta to the m. Okay, so that proves part one. So basically, once the kernels have stabilized, images have two. But we still need to prove two, which was saying that we have an internal direct sum. Okay? And just to say that we are proving something here, if you haven't waited for this stabilization to occur, so if you haven't gone up to the end pad, this is just not true. For example, our previous linear operator, our C2 to C2 one. In that case, if you take away the m, the kernel of the, well, theta minus I, the thing we're looking at for eigenspaces, that was 1, 0, I think. But the image would also be 1, 0. So it would be, an external direct sum would be fine, but it wouldn't be an internal direct sum. Okay, so it's really crucial that we've waited until our theta, our kernels and images have stabilized in those chains. But let's check that. So that should come up in the proof somewhere. So for 2, by the rank nullity, we certainly have a statement about dimensions. So to prove that it is actually a direct sum, internal direct sum, we just have to check that there's nothing that's in both the kernel to the nth, the nth kernel thing and the nth image thing, except the zero vector. Just need to check that the kernel of theta to the m intersected the image is 0. Trivial. All right, so let's do that. So your B is in both. First of all, theta to the m of V equals 0. That's because we're in the kernel of theta to the m. And secondly, there's a W in V with theta m of W equals V. But then we can look at what happens to theta of V, theta to the m of V. which is 0. Move it over a bit. But now put in V, what V is in terms of, this is theta 2m of W. So W, what that says is that W is in the kernel of theta to the 2m. But because the kernels have stabilized, this is the same as the kernel of theta to the m. That's the key little point. So in fact, V equals theta m of W, that was what V was, but this guy's in the kernel of this, so V had to actually be 0 after all. Okay, so just the little trick we did was this exactly here. So the corollary to that, is that okay? The corollary to that is an exercise just in checking through a few little things. As soon as the kernel of this thing is stabilized, then that is the generalized eigenspace. Okay? I mean, there's not much of an exercise here. I mean, it's clear enough, right? I mean, you're looking to be in the generalized eigenspace. There's meant to be some sufficiently high power which kills you, but as soon as these two kernels have agreed, then any high power does the same thing, kills exactly the same elements. Okay. So it's not much of an exercise to do. It's straight away from what we just said. But so that gives our actual technique to compute a technique to compute the generalized eigenspace. Let me quickly say that. We'll come back and do an example next time. The strategy is really, in essence, it's just to keep computing these kernels. So the first kernel there is just the eigenspace. Great, do it. Then find this matrix. So square the previous matrix you had. Find its kernel. Good. Keep going. If it didn't agree with your old kernel, you have to keep going. As soon as those two things match up, your previous kernel and the next kernel you compute, then you're done. That is the generalized lambda eigenspace. And just to say something, this certainly occurs for some m less than or equal to the dimension. That just comes from when we're looking at those kernels, they can't just keep being strictly increasing past the dimension. So at some point it happens before that, but that's still not a great bound because, working in a 7-dimensional space or something, you might have to go up to 7. You can say something a tiny bit better, and I'll say that and then conclude for today. There's one further observation that saves time, and we'll see this a bit later. We don't see it right now. But if the multiplicity of lambda in our characteristic polynomial, so the number of times that root x minus lambda was repeated, if that is d, let's say, then the dimension of the generalized eigenspace turns out to equal d. So we'll emphasize that again later. That's very important. So it gives us another way of knowing when to stop. You just keep computing these kernels until you get dimension d. Just slightly more efficient because you don't have to do the extra 1 to check that it's stabilized. As soon as you get dimension d, that's it. And when you're below dimension d, you know you have to continue because of this thing in the red box. Okay, so that's a lot for today. When we come back tomorrow, we'll actually work through the calculation of generalized eigenspaces and take it from there. Okay, see you tomorrow.
Well,